The proper selection of a distribution substation transformer. Hello everyone, my name is Rafael, I'm an electrical engineer, and in this video we're going to speak about the proper selection of a distribution substation transformer based on a needed load and the forecasted load growth. And to do so, I brought this exercise. I left the statement of the exercise in the description of the video. Let me read the problem. Assume that one distribution transformer of a substation supplies 3 primary feeders. The 30-minute annual maximum demands per feeder are listed in the table together with the power factor at the time of annual peak load. So these are the values. Assume a diversity factor of 1.15 among the 3 feeders for both real power P and reactive power Q. Letter A, calculate the 30-minute annual maximum demand on the substation transformer in kilowatts and in KVA. Letter B, find the load diversity LD in kilowatts. Letter C, select a suitable substation transformer size if zero load growth is expected and if the company permits as much as 25% short time overloads on the distribution side of the substation transformers. Among the standard 3-phase transformer sizes, those are available. So these are the transformer types available, where SC means self-cooled and FAC means forced air cooled. Okay, these are the values for self-cooled and the values for forced air cooled. And lastly, letter D, now assume that the substation load will increase at a constant percentage rate per year and will double in 10 years. If the 7,500, 9,375 kVA rated transformer is installed, in how many years will it be loaded to its fan-on rating? Okay, this is what the exercise wants us to calculate, and this is what we are going to do. Firstly, we are going to calculate what letter A wants. Letter A wants us to calculate the 30-minute annual maximum demand, and to do so we are going to use the diversity factor. FD is equal to the summation of the individual loads or individual demands divided by the diversified demand. Okay? So we sum these values and we divide by the diversified demand. It's 1,800 plus 2,000 plus 2,200 divided by the diversified demand, and this, as the problem says, has to be equal to 1.15. Okay, very easy, very easy. Therefore, DG is going to be equal to, I pass this there and this goes dividing, 6,000 kilowatts divided by 1.15, and this is equal to 5,217 kilowatts, and this is equal to the real power. So save this value Okay, it's going to be important, and we are going to use it later to calculate the apparent power. Okay, to find the apparent power, it is required to work on the power factors. We are going to use this and the power factors to calculate the apparent power. Let's go. It is going to be easy. Stick with me and we are going to do it. Okay? So let's continue. Okay, first of all, let's use this power factor here, 0.95. Theta 1 is going to be equal to the inverse cosine of the first power factor, 0.95. Isn't it? Easy. And then we find an angle of 18.2 degrees. Very cool, isn't it? Now we find the second angle, theta 2. And this has got to be equal to the inverse cosine of 0.85. And this is equal to 31.79 degrees. Okay, my friends. I think you guys are learning it because you can see it is easy. Let's go to the third angle, theta 3, which is equal to the inverse cosine of 0.90, which is equal to 25.84 degrees. Right? Do you guys get it? Very easy, isn't it? And now, we can use these values here to calculate the reactive power Q. And so let's go. Let's calculate the reactive power. Save these angles here. I am cleaning here the board, but save these angles because we are going to use them just now. The diversified reactive power, Q, can be calculated as Q is going to be equal to the summation of PI, the individual real powers, times the tangent of the angle. I, the angle that we found, divided by the diversified factor. Okay? Very good. I'm gonna do it slow so you guys will understand everything. And then we find that Q will be equal to 1800 times the tangent of the first angle, 18.2 degrees, plus 2000 times the tangent of the second angle, which is 31.79 degrees, plus 2200 times the tangent of the third angle, 25.84 degrees, and this all has to be divided by 1.15. Okay? Very easy. If you understand this expression, it's going to be easy for you to come up with this. And then we find a value Q equal to the diversified. These are the individual values. This one, and this one are the individual values. And the diversified reactive power is 2518.8 kVAR. Did you guys understand the difference between the diversified reactive power and the individual reactive power? Okay, If you understand this, I can go to the next step, which is to calculate the diversified apparent power. And the diversified apparent power, or the demand, will be equal to, so let me erase this again, save these values here, okay, and then check later. It's going to be important for your learning to try to practice. Do it yourself, try to practice. Okay, so the diversified demand or the apparent power will be equal to P squared plus Q squared and the square root of it all. The square root of P squared plus Q squared. And if you use the values that we dealt with, the diversified real power and the diversified reactive power, we get this. 5,793.6 kVA. Okay. And with this result, we finish letter A. And now, let's go to letter B. Letter B is a lot easier. So letter B, we do this to find the diversified, to find the load diversity. Letter B wants the load diversity. To find the load diversity, we use the expression LD is going to be equal to the summation from 1 to 3 of the individual loads minus the diversified demand. And it is equal to 6,000 minus 5,217. And LD, load diversity, is equal to 783 kilowatts. So the load diversity is 783 kilowatts. All right, let's continue. Let's continue with the exercise. Now let's move on to letter C. What does letter C want? Us to calculate from the given transformer list. We are going to work on this. To the given transformer list, is appropriate to choose a transformer with the rating 3000. We are going to choose this 3750 4,687 ratings. Since with the 25% short time overload, it has a capacity of, let's calculate, 4,687 times 0.25, okay? 25%. Yes, that's what letter C wanted us to calculate, and this gives 5,858.8 kVA. Okay? So, this rating, this 25% overload, is higher than the maximum demand. We found that the maximum demand is 5,793.6 kVA. So the maximum demand is this. And if we use the 25%, oh, sorry, here is not 0. Here is not a 0. It's 1. 1 point. Okay, now it is because you want 25% above. You want 25% above this number here. So 25% above this number is this, and it is larger than the maximum demand. So we can use this transformer here. This transformer may be cheaper. We don't need to buy a more expensive transformer. We can use the cheaper one with a lower rating, and we can still satisfy the demand, okay, without having flashovers or any kind of problem with the transformer. All right, so this is what we are going to choose. This guy here, we are going to choose it. Okay, and then to finish, let's go to letter D. Letter D talks about what? Letter D talks about an increase. We are going to use this transformer here, this rating here, as the exercise wanted us to use. We are going to use this rating here and see how long will it take for, as we are dealing with a growing demand, how long will it take for it to be loaded in its full capacity. So note that the term fans on, so this is self-cooled and this is forced air cooled. Fans on means this, forced air cooled. Okay, note that the term fans on rating means the forced air cooled rating. To find the increase per year, let's do 1 plus G to the 10th power has to be equal to 2. Okay? Is the increase per year. And then we continue and it goes like this. It's the 10th root of 2. And then we do some manipulations here, very simple algebraic manipulations, and we get that G is going to be equal to 0.07175, or G, the growth in demand, is 7.175% per year. Okay? We discovered that the load is going to increase 7.175% per year. Okay, therefore, if we want to calculate for the transformer, this transformer here, we are going to do this. We are going to use this value here. We're going to use this value here and try to predict what's going to happen. In how many years it will be loaded to its fans on rating. All right. I think you guys are understanding everything. If you are not, please read again the statement of the exercise, because the first thing that we need to do to solve a problem is to properly understand the statement. Without understanding the statement, we are going to start calculating a bunch of things without knowing where we want to arrive. So our objective is to understand the statement of the exercise and later start calculating. So I want an increase of approximately 7% per year. So 1.07175 raised to the nth power times 5793.6 is equal to, this is the maximum demand, 2 times, no, sorry, it's 9375 kVA, because we are working with this. We want to know in how many years or how many months, how long will this get to this based in this load growth. We have a load growth of 7%. I want to know how long will it take for this maximum demand to reach the maximum demand of the transformer, the maximum apparent power of the transformer. And then we apply the logarithm here. We pass this dividing there. We apply the logarithm. And then we find that n is going to be equal to the logarithm of 1.6182 and log 1.07175, which is equal to 6.9. We are going to use it approximately, okay? Approximately. Approximately approximately 7 years. Okay, so this is our final result. Ultimately, this transformer here, based on this maximum demand, will be loaded to its fan-on rating in about 7 years, okay? So guys, this was the video that I wanted to make. It was a very nice video, very good video for people that want to work with distribution, engineering, electric power distribution. And I hope you guys understood and learned from it. If you want to talk to me, I'm gonna leave my WhatsApp number, or you can simply drop me a message in the comments of this video, okay? My friends, goodbye!